So the cable C to D, so where is the cable? Right here. They give you the orientation of that cable. That cable looks like it's going to be in severe tension because of the downward forces applied. But the cable can sustain a maximum load of 1,500 newtons. Determine the maximum load F1. So what is this maximum F1 and the magnitude of the reaction at the pin A? Well, what we would do is we would create a free body diagram of that rod. And you want to definitely be careful about cutting. I have to cut through the cable. There's a force in that cable, a tension force. And so that's going to be exerting a force. Maybe I move that down a little bit. And you can even add to the free body diagram, the orientation, the 3, 4, 5 triangle to help you with that force. And this is an unknown force, but it's going to be set to the maximum of 1,500 newtons for the calculations. Okay, and then we're going to have our F1, and then 1/2 of F1, 1/2 of F1 coming down. And then we have our pin. And it's pinned at A, so we know we have to replace it when you cut through. You know, it's like this. Actually, maybe I shouldn't cut through those forces. Cut, include the 2 forces, and then come like that. So we cut through the cable, cut through that pin support, and we're going to have then maybe ace of X and ace of Y. I pause. Do I have a good free body diagram? I could put more information on there, like, and probably should, like this 30-degree angle, maybe like the dimensions, 1.5 meter, 1 meter, like that. How would I then solve for F1? Well, for equilibrium, we'd do the sum of the moments around point. What point would you like to pick? If it's equal to 0, about any point, but particularly about point A, you'll get one equation, one unknown, and you'll be able to solve for F1 is around 1448 Newton. 4 significant digits, if I want to round it off, 1450 Newton. Then the next part of the question, what's the magnitude of the reaction at pin A? Well, if you do for equilibrium, the sum of the forces in the X equal to 0, that'll allow you to get ace of X. And then sum of the forces in the Y equal to 0, that'll allow you to calculate ace of Y. Knowing both ace of Y and ace of X, I can calculate the magnitude of the force at A, or the reaction support at A, the square root of AX squared plus AY squared. True? And this comes in at a magnitude of 1750 newtons, good to 3 significant digits. So that problem's done. Hopefully you can do a problem like that for the exam. Press forward. So for this problem, it asks us to replace the force system acting on the post by a resultant force. Let's pause for a minute right there. How many forces act on this post system? There's 3 forces. We can number them. They didn't label them or number them, but you could talk about F1, you could talk about F2, and you could talk about F3. So you're going to replace those 3 forces by an equivalent resultant force. Continuing to read now, and specify where its line of action intersects the post A to B. So this post is A to B, measured from point B. Well, you're going to measure that resultant force. May be a force that looks like this. It has a magnitude and some orientation, let's say theta. I think it's going to be pulled upward because of this 500 newtons and only 250 down, so it's probably upward directed, the resultant force. And because it's 300 newtons in the negative x, and you know, the component of that 500 newtons in the negative x probably overwhelms the 250 in the positive x. So it's probably in the positive y and negative x. That's why this theta is going to be greater than 90 degrees. That's going to be the force resultant. So you want to place it somewhere where it intersects the line from B down toward A. Let me see if I can draw that a little better. B down toward A, and maybe we'll call that point where we would apply that resultant force on this system, F of R, with that orientation theta. We would call this distance from B toward A maybe x measured from B, xb. That's what they're asking us to solve for. I know the words can be confusing, but that's what we're asked to solve for. What is the criteria for this F of Rx and F of Ry? How do you calculate the components of the resultant force, then get its magnitude, then get its theta? What's the strategy for that? Yeah, it's just the sum of the forces. So the resultant force has to be, I know that this is now a vector, I drew it as a vector, is equal to the f of 1 as a vector plus f of 2 as a vector plus f of 3 as a vector. And this is a good review because, you use this 3, 4, 5 triangle to pick off the components of the force, first force. Use an angle to pick off the components, decompose it into x and y components. And this one is purely in the x, but notice that the direction is shown. It's in a negative x direction. We typically stay with x and y coordinate system. All right. So when we do that, we come in with the force resultant, the magnitude. F is equal to 542 newtons. And this angle theta for that resultant force is very large. Theta is 169.4 degrees, meaning it's almost 180 degrees. So I've exaggerated it should be even closer to that negative x-axis. So that's the first part. Okay. Then the second part, how do I find x of b? Well, we want it to have the same tendency, not just to translate, force makes an object want to translate or move linear motion into x or y, but also rotate. And so since we suspect there'll be some support here and there'll be some moment there, but anyway, you could do it at any point. You could do some of the moments around point B for the equivalent resultant system equal to some of the moments around point B for the original system. Either way. So you can do, again, let me try and repeat that. I'm sorry. Yeah, the sum of the moments around a particular point. We could pick point A for the original system. What do I mean by original system? The 3-force system must equal the sum of the moments around the same point, the sum of the moments around the same point A for the resultant system. Now you say, well, there's only one force in resultant system, so it's really not, there doesn't need to be a sum. Okay. Does that make sense? That's our basic equation. You could say, the sum of the moments around point B for the original 3-force system, that must equal the moment around point B that our single resultant force generates around point B. That's the equivalent system. That'll work. Both of those will work. And when you go through the math, it's a good review of how to calculate moments of forces. You'll find that distance x of B is equal to 2.172 meters. Good? Press forward. So let's press forward. Somebody requested a solution to this problem. So what do we have? We have a rod that is supported at points A, B, and C by journal bearings. Well, here is A, and you can see the journal bearing. B, the journal bearing, and C, the journal bearing. Now this rod isn't straight, it's bent. It comes out, does a 90 degree, goes down, does a 90 degree, and then ends up here. So it's not a straight rod, but it's still a rod that's been bent. And those are the 3 journal bearings. The bearings are properly aligned, so they only exert reaction forces, no moments on the rod. That's good. Okay, so the alternative again would be that sometimes if a bearing isn't aligned, it could generate a moment. Just like a hinge can generate a moment, but you don't really want hinges to be generating moments. Calculate the magnitude of f of 2. So where is f of 2? Down here. And you only want the magnitude, even though it is a three-dimensional system, x, y, z. And so you're going to have f2 in the x, f2 in the y, f2 in the z. But anyway, you just want that magnitude of f2 that will cause the reaction cy at the bearing c to be equal to 0. So this is the direction, and our notation is cy would be the magnitude of the reaction force created by that journal bearing on the rod at c in the y direction is equal to 0. So that's our criteria. Well, so what's the strategy for solving this problem? Well, what exactly are we asked to solve for? F of 2. Is there only one thing, one number I'm asked to solve for? Or are there multiple things I'm asked to solve for this problem? If you're like me, you reread the problem statement 2 or 3 times till you're really comfortable. What exactly are we? We're only asked to solve for one thing. That's just F2. So we can see that we probably want to generate a free body diagram. We'll generate a free body diagram of the rod. And I'm going to reuse this illustration in 3D because it's really hard to sketch it and do it justice. And I'll do it with color. So we already did the CY. Maybe I even increase the size of the pen. Try this. There's our reaction CY. Hey, I gave you a piece of paper, didn't I? Let me ask you to do what I'm doing on the piece of paper for this. And go ahead and draw it on the illustration. Okay? I know that's recycling this, and you really should get good at drawing it off. But in the interest of time, draw it on this illustration. I'll come around and take a look at what you got. All right, so a lot of you have it, or nobody that I've seen didn't have it. So C sub z is equal to something. Let's just leave it off. We'll have to calculate it if we need to. Then we have b in the x, b in the z. Then you have a in the x and a in the y. This force is applied to our system, so it's part of the free body diagram, the force on it, as well as this one pulling down and away. True? Okay. Now, hopefully that illustration is clear. Let me ask some questions about it. This force F1, we're probably going to have to describe that in 3D. So you can think of F1 as having some F1 in the xi plus F1 in the yj plus F1 in the zk. Those 3 components, I, j, k components of the force F1. Now I'm going to say that one of those components is equal to 0. So the question is, answer A, clicker answer A, if you think F1x is equal to 0, or answer B, if you think F1y is equal to 0, or answer C, if you think F1z is equal to 0 for the information given in this problem. We know the magnitude of F1 is 300 pounds up here. All right, everybody's in. Let's take a look. Now, a lot of us are correct, but there's always a challenge for some to read these things. Why is F1 in the x equal to 0 from this illustration? Okay, and you deduce that it's in the zy plane because of, well, one of the things that you do, the angles with respect to this line. And usually when they give you those reference lines, say, oh, this green line is a reference line, and I'm going to give you 45 degrees with respect to that line. Look for which axis that green line lines up with. And it lines up with the y, not the x, not the z. And then they give you another reference line right here. That reference line lines up with the z. So there you go. Now, this could be, let's say that somebody wanted to get rid of these four lines around here. What would it do for the red vector to now be in the what is this, the xy plane? Can you see that all they would have to do is change the slopes of those lines that I tried to rub out? True? Yeah. See, if they somehow put this line right here and took it up and put it like this, now it's almost perfectly aligned, isn't it? But let's say it's not perfectly aligned. And then what you do is you come back here and you go like that. And you say, oh, well, that's the z, and this is aligned with the, not that way. How would I do it? Come in with this, right? Where that line is aligned here. And this one's aligned there. And it would be hard to make it look like it's in the x, y plane. But without changing that vector, you change these lines around it to help show its orientation. Okay, now, why did I spend so much time on that? Well, you tell me if you see a flaw or something that if I was the technical editor for the textbook, I would say, I think the graphic person needs to fix this. Can you see it? I'm going to walk around and I want you to show me on this illustration where this is very rare. This book's in the 14th edition. It's very clean. It's very hard to find errors in this book or things that could be improved. But there's something. Can you find it? I'll walk around and you take your pen and show me on the paper when you find it. All right, so let's pick it up here. So basically, this line matches the z-axis very nicely, but this reference line with the darker blue triangle does not align with that x-axis, and that's what the author or the illustrator is trying to show. And so they should have maybe tilted it back a little more like that to show that it's lined up with the x. That little bit, I think, can sometimes confuse a student because in 3D it's really hard to do that correctly. But this darker blue triangle, right, isn't that darker blue triangle in the y-x plane? What you have to do to solve this problem is you have to get the force vector F2 expressed in something I, something j, something k, the components. And if you want, you could think about getting a unit vector, ijk, and multiply by the single magnitude. See, it's like this, right? So what are those components of the I, components of the j, components of the k? And I'm going to say that you're probably going to have to worry about that plus or minus sign on all of those, figure out which they are. And then you're going to have to be using these angles 30 degrees and 45 degrees. Oh, probably the sine of this one times the cosine of that one, or maybe just the cosine of it or the sine of it. Can you figure this out for me, please? Work it out. I'll walk around. Professor, the last day of class is supposed to be easy. These questions. All right, I'll pick it up here. So this component right here is going to be the plus, so it's not a negative quantity. The cosine of 45 times the sine of 30. I didn't leave enough room. This is going to be plus. Then it's going to be the cosine of 45 times the cosine of 30. And this one here is the negative. It's in the negative z, so it's negative sine of 45. All right. I know now how to represent F1 and F2. I have my free body diagram. I have how many equations can I get maximum off of a free body diagram in 3D for equilibrium? How many equations can I get? 6. I can get equilibrium, some of the forces in the x, y, and z, some of the moments about the x, some of the moments about the y, some of the moments about the z. Those are 6 equations I can get. How many unknowns do I have? I better count them. So I have 1, 2, 3, 4, 5. I erased some of those, didn't I? Sorry about that. And then we want the magnitude of F2. That's our 6th. F2, the magnitude of F2 is our 6. 6 equations, 6 unknowns. This is not a pretty picture. This is a challenge. But you know how to do it, don't you? So what you do is you get the sum of the forces in the x equal to 0. You get an equation. There'll be a few participants. Maybe not all 6 of the unknowns are in that equation, but multiple ones are. And then the sum of the forces in the y, sum of the forces in the z, and the sum of the moments. Now here's a choice. You can just do it about the standard x-axis equal to 0, or you could do it about any x-axis parallel to the one going through the origin. My suggestion is stick with the basics. Put it all through the origin. All right, some of the moments about the y-axis going through the origin, some of the moments about the z-axis going through the origin. There you go. None of our calculators solve a 6 by 6. I think the highest somebody showed me they can do a 4 by 4. What's the probability of having a 6 by 6 on a time-limited exam? Really low. Okay? But I'm glad you do some of these for homework. Okay? All right. So in the interest of time, we solve, and you can solve for the magnitude of F2 is 674, and the units are pound. Ready to press forward? All right, let's press forward. So we kind of move into another chapter, and this problem comes from structural analysis dealing with trusses. This is a truss problem. So it says determine the force in members. How many members do they request? LK. Let's find LK, that member. BK, BK right there, and BC right there. Of the truss, and state if the members are in tension or compression. Well, should I use the method of joints or the method of sections? Sections, but I'm only asked for 3. I'm glad it's not solved for every member, you know, in the truss, tension and or compression. So I will cut like this, and then I will either scoop and cut through the support to the left, or I can get a section with the 3 forces and the support to the right. It's your choice. So which section do you like? Do you like the left side section or the right side section for continuing on? Yeah, I think the left, it has the fewer entities, a little simpler. So this one, we go ahead and try and draw our section. Now, when I came in, I get a little sloppy, but I'm going to cut that member really close to L. Then I'm going to cut that member close to B, cut that member close to B, include this force, and then cut through the support, and then continue through the air. So basically, it'll boil down to just this little triangle. And then I have a force, and I'm going to assume everything's in tension initially. So we're going to have the tension force in member LK. Then down here, we'll have the tension force. It's a little steeper, isn't it? A little steeper slope. The force in member BK, and then the force in member BC. And let me do this. Is that everything for the free body diagram? How about you draw the free body diagram for this section, and I want to inspect it. I got most of it. All right, so let me finish this. I should have asked you to start and do the whole thing, but I was particularly, a lot of people are not going to miss the supporting pin at A. They're going to put in that ace of Y, and they're going to put in the ace of X. No problem there. But a lot of people, or some people, may forget 1 5 kilonewton load. Because it's applied to B, you have 1 5 kilonewton load. Don't forget when you're doing method of sections on trusses to make sure to include any loads that are pertinent. All right? Where again did we cut? In this member, a little to the side from L toward K, but it included L in it. Likewise, it included, and so it included B. It included B, so it includes the 5 kilonewton load on it. There you go. Now it's pretty easy. If I want to solve for 1, 2, 3 unknowns, I'm going to have 3 independent equations, equilibrium, 2D. I'm going to have the sum of the moments, sum of the forces in the X, sum of the forces in the Y equal to 0. Only choice is where do you want to do the first sum of the moments? Can you see where you would maybe pick to do the sum of the moments to get one equation with one unknown? Where would you pick? Where? K is a good one because both of these go through K. So if you pick K, that'll work. And you'll then solve for, so if I do sum of the moments through K is equal to 0, I'll be able to solve for F, B to C. All right, sum of the moments through another point other than K must be equal to 0, and I'll be able to get one equation, one unknown, and solve for another one. Which one? Okay, if we do A, then what two go through A? This force L to K and B to C go through A, don't they? I'll be able to solve for F, B to K. One equation, one unknown. All right, there's another one. Sum of the moments about a particular point equal to 0. We already were able to solve for B to C, B to K. If I want to solve for L to K, force L to K right away, where would I do the sum of the moments about? Around point B. Around point B. Maybe I should have labeled B. This is point A. This is point L. Very interesting, actually. You could do 3 sum of the moments, forget the sum of the forces in X, sum of the forces in Y, and you could solve this problem completely. You can. But once you pick out one of those forces using one of these equations, most students would just use this once, then go here and here and be done with it. All right? Hopefully that all makes sense. I encourage you to practice. Let me give you some numbers. This is going to be negative 18.6 kilonewton. What does that negative mean? L to K is in compression. Okay. B to K. B to K is 6.01 kilonewton positive, hence it's in tension. This is in compression. And force, didn't leave enough, let me draw it down here. That gives us force B to C, comes in at 11.6 kilonewton, and it's positive, so it's in tension. All right. Yes? Okay, yes, you're right. I skipped that point. Okay, do a global system. If you do the sum of the moments around G for the entire truss, you'll have just AX and AY. If you look at it, we only have vertical loads. So what is AX going to be equal to? AX will be 0 because of the global truss. Also, I forgot to emphasize, what type of support is that A? Pinned. That can supply both AX and AY reaction. But this is a support at G. What type of support is at G? Is it a true pin? It's a rocker, isn't it? It's a rocker, meaning it can only support it in the vertical. It'll allow it to expand horizontally, contract horizontally. That's what you see in a lot of civil engineering, structures. Because of things expand when they're hot and contract when they're cold, you can have little rockers on bridges and stuff. So that's what they have on the truss of a bridge. So this is only G and the Y. Yeah, I would, to get A. First of all, if you do the Freebody diagram, there's not, AX is 0. on the whole truss. Now it's just AY, sum of the moments around G to give AY. All right. And I forgot to calculate AY and put it in. That was actually needed before I went to the method of sections. All right. Thank you for that reminder. Let's press forward. Determine the reactions at the supports A, C, and E of the compound beam. Well, okay, we want to see. There's a beam. It's a horizontal structure. That's what typically describes a beam. It's compound, meaning it's not all one section. It's got this section that goes in. What happens at B? What type of connection between the two sections is there at B? It's a pinned connection at B. Likewise here, it'll allow this section to rotate relative, or that, not pull away from each other or move away from each other, but rotate around D. Okay, now that's a compound beam. How many sections? It looks like it has 3. What about this support at A? What's happening at A? I understand B and I understand D, but what's happening at A? Fixed support. It's like cantilevered there. So it's going to be able to resist not only with a non-zero AX or non-zero AY, but also a reaction moment that support provides to that end of the beam for fixed support. Okay, let's take a look at C. What's happening at C? I know the illustration is a little challenging, but what is that? It's a rocker. Right, that's exactly right. It's a rocker, as well as at E, a rocker. Okay. So they want to determine the reactions at the supports A, C, and E. How many unknown scalar entities that I'm calculating, and what are their names? Let me ask you to do that. Write a list of what am I asked to solve for. Give me the symbols and then count them up. How many are there? It's not just one. It's A, C, and E, but it's the reaction. All right, so let me go ahead and summarize. So at the support A, we have AX is a reaction unknown, AY is a reaction, and then we have the moments at A. This is like in the Z direction. Here is our X, here's our Y. What's coming out of the page? The Z. And so a lot of times we draw it like maybe this or that moment. I'm going to draw it in a second, but that's our M sub A, unknown at that support, that fixed support. And then we have C in the Y, maybe you draw it that way, and E in the Y. Maybe you draw it that way. Now, I count them up, 5 unknowns. If I do one free body diagram, I'll have, with one free body diagram, I can have 3 equations. I'll have sum of the forces in the X equal to 0, sum of the forces in the Y equal to 0, and sum of the moments around a particular point equal to 0. I'll have 3 equations, 5 unknowns. Mathematically, that's not going to work. So how do I get more equations? More free body diagrams. So how many free body diagrams are you going to get? 3, right? So draw those 3 free body diagrams, please. I need 3 of them. All right, so let me pick it up here a little bit. So I'm going to have a free body diagram for this member A to B. And I'm going to come in here and I'm going to cut. When I cut through that wall at a little support around A. And then I cut through the pin at B. And so I'll have the member like this. Maybe I just show it like that. And it'll be, here's A. And then I'll have A in the Y support. I'll have A in the X support, and I'll have that non-zero moment at A. This. I tried to, when in doubt, show them in a positive sense. Did I show all 3 of these in the positive sense? Yeah. Okay. Then I come over here to B. Now I'm a little lost a little bit. Maybe I put B like this, BY up, or maybe I show it like this, a BY up, or I'm not certain exactly the direction of BY. So I can delay that on my Freebody diagram for a minute. I'm going to come over and I'm going to draw for BCD. And here's point B. Now look at point C is not in the middle, is it? As some people immediately put point C right in the middle. But it's not 3 meter, 3 meter, it's 4 meter, 2 meter. So it's a little bit off to the side for point C. All right, now I'm going to draw kind of the last one. This is D, then this is E, and this is F. Because I think it's easy when I see, oh, I have pushing down here 12 kilonewton. That support is E, and the Y is definitely only going to be supporting pushing up. That's what a rocker does. And so I look at this, what's the load on that member D, E, F? What about D? Is that the sense, the direction? Or maybe you want to draw it like this. D and the Y. True? Yeah? All right. We could also have D in the X. True? But right away, you can do some of the forces in the X on this illustration. And I've got that one nailed right away. So I know another instructor may say, you need to prove that dx is equal to 0, so you need to put it on the free body diagram. I'm not going to be that picky, okay? I'm pretty picky, but I'm telling you there's others more picky than me. But I can tell dx is 0. So if you wanted to, you could come in here and put dx equal to 0. Now, because I had dy pushing down on the free body diagram on the right, what about the free body diagram for BCD? Equal and opposite? Yeah, so it's like pushing up. That's dy. Same magnitude, different direction on different free body diagrams. How about this C? This is going to be C in dy. It's a rocker. Then we have B. B is, I'm going to look at it for a minute. I'm probably going to be pushing up because I have this distributed load. I'm going to replace it by a point load. A lot of you did the math already. You said, look, it's going to be 3 meter, 3 meter in the middle. That's the uniform load. I'm going to replace it by equivalent point load. And that magnitude is 3 kilonewton per meter times 6 meters. So that gives me 18 kilonewton down. Okay? Somebody says, well, probably I should draw that free body diagram twice. You know, once with a distributed load, then move to a new one where I simplified it. Yes, you could have a more picky instructor in the future, but I'm not that picky. I can see what you're doing. Likewise, you can put in here the b sub x, or leave it off, in my opinion, because that's 0. Because you calculated d sub x is 0. Make sense? All right. Now we go over here. Now I know the right direction for this b, isn't it? If this is b sub y is pushing up, then this is b sub y pulling down, equal and opposite. I pause. Ask me a question or give me a thumbs up if you like all three of these. You like it? She's ready to go. You're good? You're good? You're good? You're good? Perfect. Let's move. So it looks like I would come over to this system right here. What would I do if I did the sum of the moments around point D equal to 0 for, what would it give me? Wouldn't it give me E sub y? Yeah, and that E sub y comes in at 18 kilonewtons. All right, then I would do the sum of the forces in the y. What's that going to give me? The d sub y. And then the d sub y comes in at, I'm looking at my notes. It's not asked for, but it comes in at 6 kilonewton. And this was asked for, so we box it. This is now solved for. E sub y is done. We keep marching. We come over here. We now know that this dy is 6 kilonewton. How could I solve for C sub y? Do the sum of the moments around B. do the sum of the moments around B equal to 0, and that you get that Cy is equal to 4.5 kilonewton. That was one of our requested unknowns. We solved for it. Box it. Do the sum of the forces in the Y equal to 0. You'll be able to solve for B sub Y, and then that's 7.5 kilonewton upward directed. So then we move over to this one. There's a 7.5, and I want to solve for these. Can I do the sum of the moments around point A? Let me pause. I'm going to ask you to solve this. This comes in at 7.5 kilonewton. That's what it does. Do the sum of the moments around point A equal to 0 and see what it gets you. And I want to pause and walk around and see what you get. What does that give you if you do that? All right. One of the reasons I asked you to do that is because it looks like a collision. This M of A right there is the reaction moment of the support. But then I say the sum of moments about point A. Doesn't that look similar? And so it can be confusing. But what we have is well, the sum of the moments around point A. First of all, I have the moment at the support. That's at A. That's one of my unknowns I'm trying to solve for. And then I have minus B sub Y times that moment arm distance for B sub Y, which is 3 meters. That's equal to 0. I solve for the moment, reaction moment at A, and find that it's 22.5, if that's right. Kilonewton meter. Be careful of the units. Some people rush, they just put kilonewton. And then you want to do this, and you're done. Got it? All right. Then the last two things, you do the sum of the forces. Let me just write them up here. A sub x is 0. Do I need a kilonewton on that? 0? No. We talked about that before. And then A sub y is equal to 7.5 kilonewton. Sum of the forces in the y. Ready to press forward? Let's go. Levers are used to create a platform scale. Determine the mass hanging from M. So here's the point M. Here's the unknown mass that's hanging. Well, you have over here a known mass of 2 kilograms, and it's hanging at a distance 45 centimeters over from there. All right, there's a lot to digest in this problem, isn't there? This is a pin support. This is a pin support. This is a pin support. I have a member that goes, is it only A to M, or does it go A to M to B? Is that one whole member? Yeah. And then this member, is it pinned with this one going horizontal and vertical, or is the vertical just kind of in the same vicinity, but they're not pinned or connected? They're not pinned or connected right here. So there's no force between them. But up here, it's pin connected. So if I look at this member that's vertical, it goes from G to B. Is it a two-force member? It's a two-force member. It can only be in tension or compression. That makes life a lot easier if you recognize your two-force members. Because, right away, because this is a two-force member, I can draw the Freebody diagram of this AMB, the member AMB, right? So here's A, here's M, here's B. All right. Guess what? I look at its pinned. I say, well, I'm going to have a possible non-zero A sub x. I'm going to have a possible non-zero A sub y. I have the weight coming down. I'm going to work in kilogram force. So let me just put that as my lowercase m weight. I know I'm doing what most people do. They talk about weight as if it's a mass, but I think we understand each other. This force coming down is unknown, number of kilos. And then right here, well, guess what? This is, you can draw it like that. I do not have bx and by. This is 0. It's a two-force member. It's only By. If you don't recognize that, you just make a lot more work for yourself. Did that make sense? All right. Do you see any other two-force members in here? Where's another two-force member? C to D. So it's either in tension or compression. But so it simplifies when I make the free body diagram for CDL. If I do the CDL free body diagram, I'll have something CX, CY. Let me just say it's in tension. So I'll have DY, but not a DX. And then I'll have out here EY, which is 2 kilogram force. No, that's L. Isn't that L? That's LY. That makes sense? All right. This member right here is a two-force member as well, meaning that there's only a tension force up at F. Okay. Well, what you need to do is you need to draw free body diagrams of this member, that member. And notice that these are two force members here, here, and here. So they just are in tension or compression. And this problem breaks out and solves. So let me draw the free body diagram of EFG. Here's EFG. So if I have D sub Y up, I've assumed that's in tension. Maybe I'll put this one down and I'll call it D sub Y so they're consistent. This is the same magnitude. This is pulling down at E, pulling up at D. It's in tension, that member. All right. Then what I have is I'll have this one. Let's call it F. What is that? That's an F. F on the Y. And then put here, this is G pulling down, G in the Y, but that's equal to B in the Y pulling up. So just replace it. Just have one unknown. B, Y, the same right there. Okay. What is going to be CX equal to? Why is CX equal to 0? Sum of the forces in the X direction on that member CDL, and you're done. All right? If I know this is 2 kilogram force down, what is dy? How would I solve for dy? Sum of the moments around point C, and then you solve for dy. Let me see if I can give that to you. So this would come in at 19 kilogram force. All right. Now, once I do that, I come over here. Here's my dy, 19 kilogram force. Right? I can calculate the force that goes from right here in the member B to G. How would I do that? Sum of the moments around that point right there, which is point F. And you can calculate this to be 31.67 kilograms. Then once I have this, I come up here, I have this 31.67 kilogram force. I want to calculate M, do the sum of the moments around point A, and we find that M comes in at 106 kilogram. This is really an easy problem, but if you don't recognize two force members, I don't know, you could spend a lot of time on it, okay? Determine the clamping force exerted on the block if a force of P equal to 30 newtons, so this is where P is, right down here, it's 30 newtons, is applied to the lever of the bench vise. The single square threaded screw has a mean diameter of 25 millimeters, or a mean radius, because that's what they use in our equations developed in the textbook, of 12.5 millimeter. Mean diameter or mean radius. And it has a lead L of 7.5 millimeter. Meaning if I revolve it one whole revolution, it moved forward on those threads by that distance, 7.5 millimeters. That's what the lead is. The coefficient of static friction is 0.25 between the screw and what's it screwing into, the vise part. Okay, so we recall our simple illustration for studying these screws. We were thinking of pushing a block up a ramp. And that ramp has an overall length of 2 pi r, or you could just put pi d. They gave us d, but 2 pi r is what you're probably familiar with. And it rises a lead L, and we were able to talk about the angle theta, a normal force to perpendicular to the surface between the block, which is either you're pushing the threaded part up, that's another good way of doing it. So what we do is by moving it, you're lifting a weight. That's the notation used in the textbook. I'm trying to be consistent. Here, that weight is my squeezing force. Instead of lifting, I'm squeezing by weight W. What makes it want to move? Well, I'm applying a moment divided by the radius of that screw. How do I calculate that moment? Well, I come out here and I have this P, this load P, and this distance of 0.1 meter or 100 millimeters. So 0.1 meters. So that gives me the moment that's applied. And then if I look at what it's doing in the screw, the moment divided by the mean radius gives me that horizontal force. Now, if you're trying to tighten it, then with respect to the normal, what we have is we have the angle for that friction, combined friction force, the normal plus the tangential friction force. And we had this angle right here, which is our angle for static friction, which was the arc tan, the coefficient of static friction, mu sub s. I drop a vertical down. This angle right here is the same theta. Once I understand that diagram, which is a lot to digest, I encourage you to look at the book as well as notes. They want to know what is that clamping force. I need to calculate W. So we'll calculate theta is the arc tangent of that lead divided by 2 pi r. That comes in at 5.455 degrees. The coefficient of static friction is 0.25, so phi, the angle of friction, is arc tan of 0.25. That comes in at 14.04, so the sum of theta plus phi is 19.49. So this is our free body diagram of this block. Then you do the sum of the forces in the x. So you'll get that m divided by r is pushing it. And then you'll pick up is equal to r times the sine of the combined angle theta plus phi is retarding it. Solve for r. And for this problem, 719.3 newtons. Then go to the sum of the forces in the y. You want to solve for the lift W. That's r, what we just solved for, times the cosine of theta plus phi. And so you're able to solve for the lift is 678 newtons. That's the clamping force. Now, as soon as I take off that, right, what happens, it's not going to slide down, but you will get where it locks. and it stays in place. Vices don't undo once you let go. You clamp, once you let go of the rod, you put a lot of force on it. It's going to pinch it and hold it there. It'll release, it'll come down a little bit, and the magnitude of that clamping force will come down a little bit because the friction is going to retard it from sliding down. All right, but that's the answer. All right, now let's go back and solve another problem. The wheel is subjected to a torque of 50 Newton meter. So right here is our 50 Newton meter, and it's trying to spin in the positive counterclockwise direction on our wheel. The coefficient of kinetic friction between the band brake and the rim is 0.3. So mu sub k. All right. Calculate the smallest horizontal force that must be applied to stop the wheel. Where is P applied? Way up here. You want to stop that wheel. How do we solve this problem? Well, this is a belt friction problem. I don't see the belt. Well, the belt is that band that goes around. And we recall our equation that had like T2 is equal to T1 times what? E beta mu. Now here, because it's rotating, we're bringing it to a stop. We'll use the other K, the kinetic coefficient, mu sub K, right? All right. Now, beta, I forgot. What is beta? Well, it's the angle. So if this is a point. So for this problem, it goes all the way around. How many radians of contact between my band or belt and the wheel? 3/2 pi. 1 pi plus 1/2 pi, 3/2 pi. Okay. Mu sub k is known. Now I have to think about this a little bit. Which one of these segments of the belt has the lower tension or higher tension? And what we use T1 as our lower tension section of the belt, true? T2 is our higher tension section. So is this T1 up here or T2? I'm using 1 and 2 to be consistent with the book saying that's our tension. Is it our higher tension? Your last clicker question for the day. Answer A, if it's our lower tension, T1, in that section of the belt, or B, our higher tension. If I come in and I cut through that belt, through the air, through this belt, through the air, I can create a free body diagram. The free body diagram will be a circle. It'll have a tension coming down and a tension going over. And it'll have a moment applied. It'll also have a force at this support. Let's call it O. So O in the Y, and I'm trying not get it too messed up. O in the X to hold it there. All right, it's rotating a frictionless pin right in the middle right here. Okay, now if I look at it, this is my M. We already know it's 50 Newton meter. If I do the sum of the moments for this free body diagram, about 0.0, that must equal to 0. It wants to spin that way. The combination of this and this is going to stop it. So that's your higher tension at that section. You don't have to guess at it. You can see it in a free body diagram and a little analysis. Okay, so that's T2 up here. Let's call this T2. T2, and so this one is T1. Now we come down here, we write our equation so that we have our applied moment is equal to the plus T1 times that moment arm distance 0.15 meter equal to T2 times that moment arm distance 0.15 meter. Does that equation look good? We can replace that T2 is equal to T1 e to the beta mu sub k. This is known. Our distances are known. Angle of contact, coefficient of static friction. The only unknown is T1, and we could solve for T1. comes in at 107.14 newtons. Now, once we know that, we come over and we look at this linkage right here. Is that a 2-force member? No. But is this green one a 2-force member? Yes. And so basically when we do the free body diagram of this member right here, we're going to have a force T1, we just calculated. We'll have the support at this pin. It doesn't give a name, but let's leave it like that. And then what about this link in green link? Do you think it's compression or tension? It's going to be in compression. It's going to be like that. So if I wanted to find the compressive force in this green member, what would I do is I would do the sum of the moments on this free body diagram about that pin right there. And then that would allow me to calculate that this magnitude of the force in the link, I'll just call it link, is equal to 214.25 Newton. Come up here. If I do a free body diagram of this member, I'm trying to draw it like that. What do I have over here? I have P. That's what I'm looking to solve for. Some force at this support. And then we said this member, this force in the link was in what? Compression. So it's pushing that way. That's our force in the link, which we just solved for. Do the sum of the moments around that point. And you'll be able to get that P is equal to 53.6 newtons. All right, well, I'll be around for a few more minutes if you have any questions for me. Otherwise, we're done for today, and we'll see you on the exam, in the exam for Friday.